All right, so chapter 9 is based on writing single variable inequalities, multivariable inequalities as well. We're starting with single variable, meaning there is just one variable, in this case, x. So inequalities, okay, are written using a symbol like so, kind of like a little arrow that's either pointing to the left or to the right. In this specific example, this is read as x is greater than 4. Okay, if the arrow's facing the other way, okay, then that's stated as x is less than -2. And a couple ways to remember whether or not it's greater than or less than. Okay. Two different ways you can look at it. Here I wrote 4 is greater than 3, okay, which is obviously a true statement. One way to kind of remember is that the arrow points to the smaller number. Another way would be to turn the symbol into a Pac-Man type figure, and it eats the bigger number. Also seen people turn it into an alligator and give it teeth. Whatever helps you. Hey, Pac-Man, if you've ever played that game, maybe a little outdated at this point. But it would go this way, and it eats the bigger number. So 2 is bigger than -5. Okay, again, whichever way the arrow is pointing, okay, that's always going to be the smaller number as well. And so whenever we want to graph inequalities on a number line, since there's only one variable, we use it on a number line like so. Okay, so this states that x is greater than 2. Okay, so whenever we get x on a side by itself, okay, the number that we are left with is called the boundary point. Okay, that's going to be the point that we go to on the number line. Okay, and we're going to draw a circle on that boundary point. All right, so in this instance, x is greater than 2. So on the number line, we want to show that all of the points that are greater than 2 can go into this inequality. Okay, so where are the points greater than 2? Well, it's all the points to the right. Okay, you can draw a straight line. Okay, some people, you can draw it, especially in the textbook, you'll see it, you know, as the circle on the actual number line. It's just always kind of tough to read it if you're drawing it on a piece of paper. Okay, so I always like to do it just a little bit above, like so. And what this means is that all numbers greater than 2 are solutions to the inequality. Okay, so all of the points, you know, if the number line kept going, okay, you got 3, 4, 5, 6, 7, 100, 1,000, a million, so on and so forth. All of those points you can plug in for x, and it's going to give you a true statement. All right, you plug in 3, 3 is greater than 2. That's correct. Okay, notice the points that aren't in that shaded region. For example, 0. If you plugged in 0 for x, you get 0 is greater than 2. Is that true? Pretty sure it's not. Okay, 0 is not greater than 2. So that's why 0 doesn't fall under that shaded region. Okay, so this graph is stating that all of the points greater than 2 can be plugged in to give you a true statement. All right, so notice on this second one here, okay, my arrow now has a line underneath it. Okay, and so that changes it up just a little bit. What this states is that X is less than or equal to -1. Okay, so whenever you have an inequality with the line underneath it, like so, it means we are now including that point. Okay, and so that's going to look a little bit different on the graph. So we go to our boundary point of -1, and instead of having an open circle, we're going to fill it in to be a closed circle or closed dot. Okay, and that means we include that point. And if we want the values that are less than -1, we're going to shade to the left because that includes all of the points less than -1. You plug in -2, -3, -1,000. Okay, all those points are going to be less than or equal to -1. Okay, so open dot, not including that point, just greater than or less than. Closed dot, we are going to include that point, greater than or equal to, less than or equal to. Okay, one of them we saw look like this. I'm just sketching my number lines. Obviously, they're not exact. Usually, I want to keep a couple of important points, like the boundary points. All right, so our first boundary point at -4 is going to be an open or a closed circle. It's going to be closed, right? The second boundary point's at 2, open or closed circle. Open. All right, so if x is greater than or equal to -4, okay, that's all the points going to the right. And then I have x is less than 2, which would be all the points going to the left. Okay, and I create this little stretch of numbers right here, okay, that all fit into x right there. And this is referred to sometimes as an and inequality, because x is going to be greater than or equal to -4, and it has to be less than 2. All right, so referred to as an and inequality. Okay, our second kind of unique situation here. X is less than or equal to -3, or x is greater than 1. So we have our two boundary points. They should both be closed circles. Okay, and if we say x is less than or equal to -3, that's all the points to the left. Or x is greater than or equal to 1. It's going to be all the points to the right. Okay, and this is, again, sometimes referred to as an or inequality, right? Because the number could be less than -3, or it could be greater than 1, okay, and it would fit in there. One way we used to talk about these was like our and, or it's a rubber band. Like, it looks like a rubber band. And our or looks like oars of a boat. Right. Paddle boat. Not a paddle boat. It's the boat. Boat with oars. graphs that look like this. All right, so now kind of working the opposite way. We're given the graph, right? The inequality expression. All right, so boundary point here at 1. So we should know we have an X and we have a 1. All right, since the arrow is pointing to the right, these are the numbers that are greater than 1. Let's say X is greater than 1. And since it's a closed dot, we're including that value. So X is greater than or equal to 1. Okay, B, we have a boundary point of -1. We have X, we have -1. Since it's pointing to the left, we want the values that are going to be less than 1. It's an open circle, so we're not going to have that line underneath. So just X is less than -1. So one thing to notice, the arrow is pointing to the right here, as well as the graph. It's the numbers that are pointing to the right. Here, it's to the left. It's the numbers that are going to the left. Okay, so you can use that. Okay, the only catch is the X value has to be on the left. Okay, because we can also write this as 1 is less than or equal to X. All right, those mean the same thing. Okay, but now notice the arrow is pointing to the left. Okay, but if the X value is on the left-hand side here, like it is right now, and we read it as X is greater than or equal to 1, you can use, okay, the arrow is pointing to the right, so my inequality has to point to the right. I don't really love teaching that because, again, could end up with the X on the right side of the inequality and it throws everything off. But if the X is on the left side, then that works out. Okay, letter C. Is this going to be an and or an or? Or, right? Oars of a boat. All right, so we know we're going to have an X or another X. So we got our two boundary points of -3 and 2. All right, so if these are pointing to the left, I want numbers that are less than. So X is going to be less than -3, or it's going to be greater than or equal to +2. And then in letter D should be an and, right? It's a rubber band. So we have our boundary points of -4 and 2. And we have the X in the middle there. Okay, so our first one should be -4 is less than X. Okay, or should be stated basically as X is greater than -4 and X is less than or equal to 2. Okay, so again, you kind of have to read it awkwardly, okay, because if you read this first part, you're basically reading from the right to the left, which is uncommon when you read. Usually you read left to right. Okay, so here we're reading right to left, so read it as X is greater than -4 and X is less than +2. Okay, last thing. Talk about today, solving a linear inequality. Pretty straightforward with one little caveat. So we got 2x minus 5 greater than or equal to 3. Okay, so all we're doing is basically exactly what we would normally do if it was an equal sign. Okay, and we're just going to solve for x. Okay, and we're going to treat this inequality like it's an equal sign. So if we want to get x on a side by itself, going to add 5 to both sides. We're going to divide both sides by 2. And we're going to get x is greater than or equal to 4. All right, so what that means is all numbers greater than or equal to 4, we can plug into this original inequality, and it'll give us a true statement. All right, so greater than or equal to 4, easy number to pick would be 5. So let's say I plug in 5. Okay, and when I plug that in, I should get a true statement. So 2 times 5 minus 5 is greater than or equal to 3. Two times 5 is 10. 10 minus 5 is 5. Is 5 greater than or equal to 3? It is. So that works out. Okay, so basically anytime you're solving a linear inequality, you're treating it just like if it was an equal sign, except with one little catch. Okay, and that little catch is in this next example. We have 3 minus 2x is less than 1. We're going to solve for x just like we would. Subtract 3 from both sides. Okay, so I get negative 2x is less than negative 2. And now I'm going to divide by a negative 2. Does anybody know what happens when you divide by a negative? It does become positive, you're right. Well, a negative divided by a negative becomes positive. Okay, but in the world of inequalities, if you divide by a negative, you flip the sign. Okay, so that's going to be big this chapter. We move on to two variable inequalities. It's going to be the same thing. Arjun? As if you were dividing by a fraction. Yeah. Multiply by a whole number is the same thing as dividing by a fraction. So yeah. All right, so we flip the sign. So now after we do that, -2 divided by -2 gives us that boundary point of 1. Okay, so if we wanted to graph it and just kind of take a look, we should have an open circle and all the values to the right. And so the good thing about this is we can always kind of check our work. Okay, maybe we forgot to flip the sign. Okay, maybe we, are unsure if we should flip the sign or not. If we have a boundary point of 1, I can check a point of 0, okay, which is not in the boundary. Okay, and I can check a point of 2. Okay, so remember, when you plug in these points, if they're in the shaded region, they should work. They should give you a true statement. So if I try 0 and I plug 0 into my original equation, 3 minus 2 times 0 is less than 1. 2 times 0 is 0. So I get 3 minus 0, which is 3. Is 3 less than 1? No, obviously, right? So since this is false, 0 should not be in the shaded region. Should not. It's a big word to omit there. Should not be in the shaded region. Okay, 2 is over here, so it is in the shaded region. So when I plug that in, I should get a true statement. Plug in 2. 2 times 2 is 4. 3 minus 4 is -1. Is -1 less than +1? Yeah. So since that's true, 2 should be in the shaded region.